All right, so the first part of this is really pretty straightforward. We've got things that are on the periodic table, pick two, the symbol, the name, atomic mass, atomic number. We talked a little bit about the three standard subatomic particles being proton, neutron, and electron. We also talked about the fact that the neutron is the largest one because of the fact that in reality, it is a proton and an electron glued together with a neutrino. This is also listed in your textbook as well as in the notes. Things that are in the nucleus, only the protons and the neutrons. There were a lot of answers that were possible for notable contributors. We talked about a various number of them. Looking up the atomic numbers, you obviously need to refer to your periodic table to do this. So we have cobalt, which is 27, palladium, which is 46, and fluorine, which is 9. Then I switched to a different piece of information from the table, atomic masses. So 14.01 for nitrogen, 52 for chromium. If you gave me the unrounded version, that was fine. And bromine being 79.9. I gave you a specific isotope. These are not necessarily the most common isotopes on a given element. So calcium 41 means you should have 20 protons and 20 electrons, but you must subtract 41 minus 20 to get 21 neutrons. I gave you the 96 version of molybdenum. There are other versions. So 42 of the protons and the electrons. Again, you must subtract 96 minus 42 to get 54 for your neutrons. For your bismuth, this was isotope 209. So 83 for protons and electrons and 126 for neutrons. All right. Some people tried to do number 9 with a division step, which is not the way weighted averages work. In this case, I gave you 3 isotopes. Yes, there are actually more. But I also gave you 3% abundances. This requires you to move the decimal place. You must move it from 14.25 to 0.1425. And the same with your other two. Move your decimal place 2 spaces to the left. Multiply your masses, the 80, the 84, and the 86, by your now decimalized versions of your abundances, and then total downward your numbers. You end up with a number that is slightly different than what most of the periodic tables will report, because I eliminated some of the actual isotopes that are available for krypton. Some people did not understand number 10. When it says name, that doesn't mean write the name, write the word 2 out, okay, as in TWO. All the groups that we talked about that have specific names, you need to apply those names. So barium is in the column that has calcium and magnesium further up the row, up the column. So it is known as the alkaline earth metals. Then I gave you a selection of elements and asked you to identify whether they were metal, non-metal, or semi-metal. This harkens back to the notes where I specified that only silicon, germanium, and arsenic can be guaranteed to be semi-metals. All the other ones we are going to consider as to be shelved as metals or non-metals. So iodine, sulfur, selenium, they're all non-metals. Calcium, aluminum, regular metals, with the arsenic being the semi-metal. charges, and I picked things specifically that were not transition metals because the likelihood of these elements having other charges is much lower. Sulfur does occasionally have other options, but this is why I said most likely. Okay, sulfur is most likely to be -2 in the ways that we have dealt with it thus far. Calcium +2, aluminum +3, rubidium, you could just write a single plus or you could write a +1. For naming, so the first chunk here, I gave you formulas and ask you for the names of them. So sodium hypochlorite, in part because the OCl is a polyatomic. Carbon disulfide, you have two nonmetals. You need the prefix to go with the sulfur. Manganese 2 sulfate. You must have a Roman numeral 2 to go with your manganese because you must specify which one it is. Manganese is a transition metal and has more than one option. Barium cyanide, magnesium sulfide, and phosphoric acid. You cannot call it hydrogen phosphate unless I had somehow specified to you that it was a gas, of which it isn't. Looking at the second column, ammonium, actually, I skipped one, sulfur dioxide, again, two nonmetals. And then we pick on the next one that has one of the much more rare positive polyatomics, ammonium sulfide. There is no such thing as hydrosulfide. I don't know what Google coughed up in terms of suggestions, but hydrosulfide is not a thing, okay? Not in any terms that actually follows criteria for inorganic chemistry. Then we've got potassium carbonate, two separate molecules there that have the need of a Roman numeral. They both contain phosphate, but because their metals are different, their Roman numerals end up being different. We've got nickel 2, but iron 3. Now, the last one does have two options. Because bi is considered a acceptable prefix in the older naming system, bisulfate is allowable, or hydrogen sulfate. When we look at the last chunk here, all of these, I gave you names and asked you for formulas. So pay attention to the endings because things that end in "ite" and "ate" must contain oxygens. Sulfur tetrafluoride, the tetra is your indication that there are 4 fluorines. Chlorine dioxide, the di being the indication for 2 oxygens. Potassium nitrate, it can't be just a K and an N, it must be an NO3, because if it was just a K and an N, or some variation thereon, it would be nitride, not nitrate, which then brings us to the one below it. Nitride has no oxygens. Iron 3 nitride. The iron has a +3 charge, as indicated by the name. Nitride has a -3 charge because of where it is on the periodic table. You only need one atom of each. Chromium 3 perchlorate. You need to have parentheses around your perchlorate polyatomic, and there should be a little 3 on the outside there to indicate that there are 3 of them. Titanium 4 iodide. With the exception of the ammonia molecule, which we haven't really talked about in great deal, you can't put the iodine at the beginning of the molecule. Titanium 4 iodide must start with a titanium atom. So Ti, I4. sulfurous acid. You need the SO3 at the end because that corresponds to the OUS ending. Rubidium peroxide, 2 rubidiums and 2 peroxide, or 2 oxygens in the peroxide. Barium hypobromite. This one does have one variant. There are a few valid sources which will list it as BRO instead of OBR. That is considered to be an acceptable variation. And then nickel 2 permanganate. Your permanganate should have parentheses and then have a small 2 as a subscript on the outside. Questions about the homework set? All right, so we've been plowing our way through parts of chapter 3. So let me find my other file and we will talk about chapter 3 stuff. And I have to hunt through my note section here. Blah, blah, blah. Share. All right. We were about 2/3 of the way through this chapter. We spent some time talking about empirical and moleculars. We talked a little bit about percent by mass. And then I think the last thing I did was the hydrate information, in part because that is the lab that is occurring this week. So some people did the lab yesterday, and we cooked our samples, we dehydrated our hydrates, and some of your data looks similar to my example here, and some of you will be doing this tomorrow. You are using this information ultimately to figure out how many molecules of water are contained within a given hydrate. All right, and then we talked a little bit, I'm going to kind of rehash just a little bit here of the molarity part. All right, so concentration. Concentration being in this semester, the version that we will spend the most time on is known as molarity. We have a capital letter M. We are using solute in solution. This is not the only variant on concentrations, but it is the one that we are going to be paying the most attention to this semester. If you have a 1 molar anything, you have 1 mole of your solute, and it is assumed to be dissolved in 1 liter of solution. This does not necessarily mean you have 1 liter of liquid and then you dump something into it, because that would make it more than 1 liter. And I briefly talked about some of these calculations before last week, before the test weekend. So we have 2 different examples here. One involves sodium hydroxide, and I used 17.4 grams of sodium hydroxide. Note, it's not in 1 liter. It's in 600 mils. So my first step is my conversion that allows me to take grams and convert it over to moles. So I'm dividing by the molar mass. 1 sodium from the periodic table plus 1 oxygen plus 1 hydrogen will give me a molar mass of 40. Do your division, you get 0.435 moles. Now you need to do your second step, which is the divide by 0.6 liters. This will give me 0.725 molar. So the other one, I gave you different amounts, okay? It also has a different molecule, so it has a different molar mass. I just wanted to make sure I gave you a couple of examples because this is a common calculation. 5 grams of copper sulfate, again, back to periodic table usage, 1 copper, 1 sulfur, 4 oxygens. This one weighs a little bit more. This one weighs 159.61, which then gives me fewer moles, 0.031. I'm going to divide by 0.12 liters. Again, I have moved my decimal place because I have converted from milliliters over into liters. Gives me a smaller concentration ultimately. I've got 0.250, 0.258 molar.
I have a question.
Yes.
So it would always be moved over to liters then?
Usually most textbook problems and most homework problems give you the volume in milliliters. So usually you are moving it. Pay attention to your unit though.
Mhm.
It is not impossible that you might be presented the information in terms of liters and then you wouldn't need to move your decimal place.
Oh, true. Okay, and then another thing is like the one we're doing right now, 159.61. So you're using the atomic mass for each of
Yes.
the elements, right?
Yes.
Add them together.
So, like for instance, if I look up copper on the periodic table, it's about 63.5, and I would add to that 1 sulfur, which is about 32, and then
And then
4 times 16, which are my oxygens, and I total all of that up.
okay, got it. Thank you.
All right, going back in the other direction. What if you knew what your end goal is, but you didn't know how many grams you needed to weigh out? When I prep solutions for lab, which I sometimes do, I need to do this kind of a calculation to figure out how many grams I'm weighing out on the balance before I add it to the liquid. So in this case, again, we're going to move our decimal place so that we have liters. So 0.250 liters. Multiply it by your molarity. And because liters are on the top and on the bottom, they will cancel out. And I will end up with moles. So 0.1875 moles. And then my second step, this time around, instead of dividing by a molar mass, I am multiplying by a molar mass. This time I picked on calcium chloride, so 1 calcium and 2 chlorines. Now I'm going to see if I can pull up a picture of a volumetric flask, if I can get Google to kind of cooperate here. Because volumetric flasks are a little bit different in structure than the ones that we tend to use for other things in lab. All right, so here's a volumetric flask. Note, the neck of it is very sort of long and skinny. And like a pipette, there is a mark on it. This one I pulled up is for a 200 milliliter volumetric flask. It's not cone shaped the way an Erlenmeyer flask is. It kind of looks like you took a teardrop and kind of squished the bottom flat. So volumetrics are marked only in one spot because each volumetric is designed for a particular size volume. And they only tend to come in certain sizes. They do go all the way down to Barbie size. You can get 5 and 10 milliliter volumetric flasks, but the traditional ones, the ones that you might see sitting around lab, tend to be more likely things like 100, 200, 250, half a liter, 1 liter. Those are more typical sizes. All right, so you would put your mass, your 20.809 grams of powdery stuff, into your flask and add a little water, swirl it so it mixes, and then fill it up slowly until you actually reach the mark that is on the neck. So if we are making solutions, we also need to think about what that means in terms of possibly ions. So the ions that we put together in order to make molecules, which we then named, we can also tear apart. I picked on silver nitrate as a fairly straightforward one. I want to figure out what the concentrations of my silver and then of my nitrate separately are in my 0.38 molar solution. So look at my little equation there. If you drop molecules of silver nitrate into water, it will separate into pieces. The nitrate does not fall into separate pieces, and we're going to circle back that again to that idea when we start the next chapter. But think of it kind of like shoes, okay? If you look in your closet and there are 3 pair of shoes, okay, presumably that means there are 3 left ones and 3 right ones. So kind of think about that idea in terms of your silver and your nitrate. You're not dividing by 2. Just because there's 0.38 molar and you have 2 ions, you're not going to do 0.38 divided by 2. You are doing it as if they were 2 parts of the same solution. So 0.38 of silver and 0.38 of nitrate. What if it wasn't just 1-to-1? I gave you here iron 3 acetate. So this molecule has 3 acetates for every 1 iron. So we've got a different ratio going on here. My iron concentration, my little Fe's by themselves, are still going to be 0.91. But think of it like maybe Legos. Okay, somebody gives you a Lego thing that has 1 blue one and 3 white ones. Okay, if you pull all the Lego bricks apart, every molecule has 3 white ones. Okay, so I need to multiply by 3 in order to figure out what the molarity of my acetate is. In this case, it's 3 times as much as my whole solution, and I end up with 2.73. So we can apply this idea to figuring out moles and atoms. So we're extending the idea that we addressed earlier in the chapter and kind of tinkering around with it and doing some extra things with it. I spent a while working for an environmental lab over in Portsmouth, which actually doesn't exist anymore. Portsmouth still exists, but the lab doesn't exist. One of the things we did was heavy metals analysis. And one of those tasks involved taking wastewater samples from places that did x-rays, okay? Hospitals these days tend to mostly use digital versions of x-rays, and even most dental practices are kind of moving in that direction. But some of the smaller individual doctor offices, some vets, some chiropractors still used traditional x-ray technology, which involves silver as part of the product in the x-ray. Well, as you're developing the X-ray, some of the silver is shed, but because it's a heavy metal, we want to minimize the amount that gets discharged into the sewer system. So usually you have a device which helps reclaim the silver by, you pour all your waste liquids through it and it traps the silver ions. So if I had a known concentration, it's kind of wimpy, 0.0031 molar silver nitrate. But I have about a gallon of it. I've got 4.5 liters. How many grams of silver could I get out of it? How many atoms? We're going to pull Avogadro's number back in here for a moment. So if I multiply molarity, which we know is moles per liter, and I multiply it times liters, and I'm going to go back over here and change this into a capital letter L so it looks a little bit more like a liter and less like a number 1. So multiply those two together, I get 0.01395 moles. But it asked me for grams. So back over to the periodic table. I have an atomic weight of 107.87 for silver. Multiply those two together, and my moles will cancel out. I don't get a very big mass. I get 1.5 grams. Decent sized nugget. That's about all you get out of it. How many atoms, though? And I just realized when I copy pasted this from something else, it ditched my subscript thing here. This is supposed to be 6.02 times 10 to the 23rd exponent. And somehow it deleted my exponent function there. So now take your moles and multiply by the fact that we know, and I should probably, let's do this. Let's do over moles, okay? Because that way moles on the top and moles on the bottom cancels out. And you get 8.4 times, and again, this is, somehow this deleted this, 10 to the 21st power as your atoms. Back early in the chapter, we talked about the fact that even if you have way less than a single gram, you are probably going to end up with a fairly massive number of atoms, usually at the very least having an exponent of the teens or maybe higher. So keep that in mind when you are looking at these kinds of problems. A variation on this is dilutions. Some of the stuff we store in the back stock room, we don't store in its wimpy form. We store it in a more concentrated form and then make a dilution the week that we are going to do the lab. It's more space efficient. So if I buy glacial acetic acid, this is the concentrated stuff, from the manufacturer. Pours a little bit like pancake syrup, okay? It's kind of thick and gooey in terms of its density. But it's also pretty concentrated in the world of molarity. It is 17.4 molar. Here's another thing to file away for useful information. You are highly unlikely, bordering on impossible, to run into molarities higher than about 30. Okay, even that's really pushing it. Most of them are below 20, and a significant number of them are below 10. So if I want to make a less concentrated version, I'm going to make some 3 molar. But I started out with the 17.4 molar. I want to make 2 liters of it. We have a little formula here. M1V1 equals M2V2. The M's are for molarities and the V's are for volumes. Because this is a not unit specific equation, you could actually do this in terms of liters, so long as you keep track of what you're doing, or you can do it in terms of milliliters. I started out this by leaving it in liters, and I went 17.4 times V, 3 times 2. My V is my unknown. Specifically, it's V1, but it's the V. 17.4 into my 6, and my volume is 0.3448 if I left it in liters, or I could move my decimal place and convert it back to milliliters, 344.8. You'd put it in your volumetric flask probably and dilute it up to the 2-liter mark. So sodium hydroxide, when we buy it from the manufacturer, it comes in pellets. However, that's not how we use it most of the time. We tend to use it as solutions, and we often tend to keep a couple of bottles of 6 molar solution around. Slightly different application, same basic premise here because we're using the same equation. If I want to make 250 mils of a relatively much weaker solution, 0.327, but I'm starting with a 6 molar. Go back to your equation again. 6 molar is your M1, V1 is your unknown, 0.327 is your M2, 0.250 is your V2. Do your math, do your algebra, multiply the right-hand side together, divide by 6. If I left it in liters, it would be the 0.0136. If I solve for what it actually asks for there in the question, I need to move my decimal point and make it 13.6 milliliters. You're essentially multiplying by 1,000. So here's another variation which we use a little bit in the hydrate lab because we are actually doing percent by mass. We're actually doing it for a solid when we're in lab, but we could do it for a liquid. If you buy cleaning products and you read the label on the back, a lot of times it will tell you, I don't know, how much ammonia, how much sodium hypochlorite, how much of other chemicals are in there as a percentage. So if I was doing percent by mass, I'm doing the solute on the top. So that's not super different in terms of the way I started out my molarity one, because I'm looking at the solute first. The only difference being this one's not moles, this one is mass, so grams. Mass of entire solution on the bottom. So both the liquid and the solid, presuming that your solute is a solid. And you're multiplying by 100 because I want a percentage instead of a decimal. So back when we did the experiment 1 a couple of weeks ago, one of the 2 options for your quote unquote unknown that you pipetted there toward the end of the lab was, one of them was rubbing alcohol. The other one was a saturated sodium chloride solution, similar to what is written here. It has a specific amount of salt dissolved into the water. If I had 1.64 grams of water, and I put it in kind of a weird amount of and I said that backwards, 1.64 grams of salt, and I put it in kind of a weird amount of water of 108 grams. Make sure you are adding your two numbers on the bottom, the 1.64 and the 108. Finish out your division and then multiply by 100. This will give you 1.5%. You could do a small variation on this that involved a liquid. If you buy a bottle of hydrogen peroxide from the grocery store or the drugstore, and you read the back, they are usually sold as 3%. Okay. So 3% of hydrogen peroxide in 100 mils of solution. If you are in the healthcare industry, they often use yet another little variant on this where if you give you an IV bag and it says 5% glucose, okay, glucose is actually a solid at room temperature when it's not dissolved. So every 100 mils that are in that bag has 5 grams of glucose. Or in the medical world, they're often as likely to call it dextrose as they are glucose. There is actually not a difference. Dextrose and glucose are the same thing. The difference is sort of medical community versus scientific community, using slightly different terminology. So I have a couple of final examples here. One that is a percent by volume, okay, in benzene in solution. So benzene, remember benzene we looked at a little bit back up in earlier in the chapter, my little hexagonal molecule. It's a liquid at room temperature. But you can weigh it, okay? You could put it in a beaker and weigh it. So if I have 30 grams of benzene in 600 mils, do your division step first, and then multiply by 100. Gives you 5% volume per volume. And actually, I just realized this was supposed to say mLs. And then the one below it is mass per volume. How many grams per how many mils? Do your division, 2.7, divide by your volume, then multiply by 100, and that one is 3.6%. One of the things that is true about percentage problems that we're used to seeing in terms of molarity is there's no molar masses in percentages. You need molar masses frequently when you are doing molarity problems. And that is the end of chapter 3. So let me talk about the homework set briefly. So I flip-flop around here. All right, so I need to find the other part. As I scrounge around and try to figure out where I stuck my original homework set problem set. All right. All right. So this is what your homework set contains. So it starts with a weighted average problem. Okay. This is something that you need to kind of keep hold of, because we saw it first in chapter 2, but the idea continues onward through into this chapter. Then we've got some various problems that involve single elements, strontium, fluorine, bromine. We have some problems that involve molecules with moles and grams, some percents, empirical and molecular formulas, solutions, molarities, dilutions, and the final, I think that's the last one on the page there. The final one is a percent by mass problem. So all of these are things that are covered by the chapter 3 notes and also in your chapter 3 textbook. So this makes homework due for chapter 3 then on Thursday midnight. So I write myself a note so I don't forget to do this after class. All right, so let's take a break now for about 10 minutes or so, and then we will come back and do chapter 4 stuff a bit. being, what are my options? And is it because I'm an adult? Is it common? And yeah, so it's like I need answers. Oh, okay. Oh, okay. And I might decide it's too complicated, or I might decide I just have an opinion. I gotta start somewhere. All right, we are switching gears to the next chapter. This is chapter 4. So in the beginning of in chapter 1, one of the things we mentioned was that reactants are traditionally written on the left-hand side and products are traditionally written on the right-hand side. There could be one or more of each depending upon what it is you actually are dealing with. So when we look at a chemical reaction, we are looking at two big things as your starting point. What are the identities of your reactants and your products? What did you start with? What did you make? But then you also need to know the relative numbers of each. Okay, think about this in terms of recipes. Okay, if I give you flour and sugar and eggs and cocoa and a little baking powder and some salt, and I say, make brownies. Okay, if I don't give you a recipe to do this with that tells you how much sugar and how much flour and how many eggs, what you create might not be edible. In the chemistry world, it might be something that doesn't hang together. You might have leftovers of one thing. You might have stuff glued together that really wasn't supposed to be glued together. So knowing how many is part of the key. So we're going to look here first at this reaction, and we're going to start with what is known as the unbalanced version. Unbalanced implies that the number of pieces on the left-hand side does not match the number of pieces on the right-hand side. And so one of the things we also said in earlier chapters was that a chemical reaction involves the rearranging or regrouping of the atoms. You don't get to make them or break them. All you get to do is rearrange them. So first we need to kind of create a little bit of a list. Okay, what did I actually start with? I've got 1 nitrogen on the left, 3 hydrogens, and 2 oxygens. I have something similar but not identical on the right-hand side. I have a nitrogen, a hydrogen, and 2 oxygens. The hydrogens are the part that doesn't match. Now, when you begin to balance things, there in reality is not one particular place that you have to start, but there are rules. You may only add coefficients. Okay, think about this like algebra. If you have 6x, okay, the 6 out in front of your x is your coefficient. If you have already existing subscripts, you can't change them or delete them, okay? If I go back up here a little bit and I go, okay, well, I could actually fix this by making it NH2 and O2 gives me NO and H2O. Yeah, no, that's not allowed. I can't change it to make it a different molecule only for the purpose of making it match, for making it be balanced. The other thing that biologists tend to violate, and organic chemists to a degree, you're not supposed to use fractions for your coefficients, okay? The rest of it ends up being kind of a tinkering back and forth thing. So I've got, and again, I'm running into this problem more every now and then when I do cut and pasty things, it deletes my subscripts and stuff. If I put a 2 out in front of my NH3 molecule, okay, well, now I've got more H's. I've also got more N's too. That sort of helps. I put a hydrogen, or actually I didn't put hydrogen. I put a 3 out in front of the hydrogen end of my water molecule. And that kind of helps, okay? It fixes one problem, but it makes another problem. Because, okay, I fixed my H's. I've got 6 H's on both sides. And I've got 2 N's. But now my oxygens don't match. So this is why I said, to a degree, it's kind of trial and error. The concept that you kind of have to mess around with your coefficients until you find a pair, a set that actually make it work out. Okay, so I ultimately decided that maybe it would work better if I used more of everything. So instead of having 6 H's, I went for 12 and put a 4 out in front of my NH3 and a 5 in front of my oxygen. And then gave myself 4 NOs and 6 water molecules. And ultimately, that's balanced. Note particularly that in this equation, I have 3 items that have even numbers, and I have 1 that has an odd number. That sometimes happens. That's the lowest I can get it and still have it actually be balanced. All right, now for Lego-y things. I'm dropping them on the floor. All right. I have two molecules here. Okay, so this one has one red, two blues, and one white. This is an identical molecule. Okay. And I want to, let's say that the white ones are chlorines. And I want to make some chlorine molecules. Because remember, chlorine likes to be diatomic. So if I only had one of these molecules, okay, and I was trying to make some Cl2s, I'm kind of out of luck, okay, because I can't have I can't even have one Cl2 molecule with only one molecule. So automatically I need two, okay? And if I pull off these two, I'm gonna kind of stick them together. There's my diatomic molecule, okay? Now I have two of the other molecules that are still partially intact. And I can say two of the original molecule makes one of these and two of those. Okay. And I didn't dispose of any molecules. Okay. I didn't get rid of any of my chunks. Okay. I didn't have any leftovers that didn't get used. You have to kind of think about it in terms of what kind of pieces am I dealing with here? So back to some more information. Some other terminology that you will see is subscripty things that are inside of parentheses. If I have an S, an L, or a G, those are states of matter, so kind of obvious, solid, liquid, and gas. And then we hit two more that probably don't look very familiar. Okay, I've got AQ. This stands for the Latin-ish word aqueous, which means dissolved in water. And I have precipitate, PPT, things that make solids. So let's take a look here at this one where I'm going to start out with aluminum, manganese, and oxygen. So in the beginning, I have a single atom of aluminum and I have one manganese and two oxygens. I want to be able to make Al2O3 and some manganese. All right, so I've got all of this stuff going on here. I've got ALs and MNs and O2s. In order to get this to work, I can't have less than two aluminums because look at the little subscript here, okay? I have to have a minimum of two of them in order to even make that molecule. So I could try to balance it by putting a 2 out in front of the aluminum, but that creates other problems. I also know that I need 3 oxygens, bare minimum, but I only had 2. Okay, so I probably need 6 to make this work. So in order to get my 6 oxygens, I'm going to have this 3 here. I'm going to multiply it by this little 2, okay, and that will give me 6 oxygens on that side. And then the big 2 multiplied by the little 3, and that will give me 6 oxygens on that side. And then I got to kind of go back and fiddle the rest of it. So 2 times the little 2 for my aluminums is where my 4 comes from. And then since I had 6 oxygens, it's dragging three manganese with it. So I need 3 on this side and 3 on that side. All right. Let me try and use my Tinker Toys again. 1 magnesium. We're going to say it's blue. Okay. 1 HCl molecule. It's white and red. I want to make magnesium chloride. So it's got to have 2 of the Cls. And I'm going to have some leftover hydrogens, okay, which look like that, okay? So, but if I only started with 3 pieces, and this is what I want to end up with, I'm holding it in such a way you can't really see. My molecule fell apart. Okay, so that's what I want to end up with, okay? And this is what I'm starting with. Well, I kind of have the problem because look at my pieces, okay? I have certain things that I have 2s of, okay? I have a need for 2 red ones and a need for 2 white ones. These are the chlorine ones. These are the hydrogen ones. So the only way I can get that to work based upon this is to double up how many of these I have. So I'm going to end up with a need for 2 of those to go with a magnesium, because otherwise I can't split them apart and end up with the right number on this side, because now I have 2 red ones, 2 red ones, 2 white ones, 2 white ones, and there's 1 blue on each side. Okay. It's all about the keeping track. So when you rewrite your equation there, instead of having 1 molecule of HCl, you have to have 2, because otherwise you don't have enough pieces in order to make the things that are on the right-hand side.
So you're making it go from like MgHCl. You have to balance it, and that's going to be your new equation.
Yes. Once your equation is balanced, chances are it now has some new coefficients that didn't used to be there.
So like, then once you balance it, let's say you have to rename them. Now you're going to name them with the proper coefficients then.
It doesn't change their name. So like, if you look at this equation, okay, it's still magnesium metal and hydrochloric acid gives you magnesium chloride and hydrogen gas. Even though I changed the coefficient in front of my HCl, I didn't change what I have. It's still magnesium metal plus hydrochloric acid gives you magnesium chloride and hydrogen gas. It's the number of them that changes once it's balanced.
Okay, I see.
So here is the unbalanced one. I've got bismuth 3 chloride and hydrogen sulfide, which is stinky rotten egg smell gas. And I make bismuth 3 sulfide and some hydrochloric acid. Now this one's messier, okay? I have to kind of look at a couple of different things. I have to look at the fact that going from the left to the right, my BIs don't match. One side has 1 and one side has 2, so that's a problem. But also, my sulfurs don't match either. Left-hand side has 1, right-hand side has 3. I can't get rid of any. The best I can hope for is make more. Okay, the making more is putting the coefficient out in front. So if I put a 2 out in front of my BiCl3, that kind of solves a couple of problems at the same time. It not only gives me the 2 bismuth that I need, it also gives me more Cls to mess around with. By putting the 3 here in front of your H2S, that will mean that I have 6 hydrogens to go with the 6 chlorines that I just made. And this 3 makes sure that I have enough S's to make my big fat molecule of Bi2S3. You kind of have to look at one element at a time and kind of tinker back and forth to figure out what numbers are best. Now, I could have balanced it with a 4, a 6, a 2, and a 12. That's balanced, but then we go back to kind of those rules that you first encounter in math when you're doing fractions. 2/4 might be a good answer, but 1/2 is better. We want to use the smallest numbers we can get away with in order to make sure your reaction is balanced. If you balance it and you go back and you skim through it and you notice that, oh, everything's an even number, then chances are you should go back and divide by 2 all the way through. So balancing of reactions is another step, okay? This is a evolution of information because we start, okay, and I'm actually gonna switch to the whiteboard for a second here. All right, so in chapter 1, we kind of introduce elements as just what they are, okay? But then by the time we get to the next chapter, we then also begin to talk about the molecules, okay? And then we name them, okay, going in both directions. And then we do calculations that are sort of grams and then moles and then atoms, okay? This is the next phase. This is heading toward taking those molecules and now writing reactions with them. So we are building our levels of information. So the AQ that is mentioned a little earlier here, this is one thing I do actually have a gripe with this particular textbook about. It gives you precious little information about the aqueous things influencing how we are going to later mix things together and make reactions happen. All right, so aqueous, dissolved in water. We know things about water. We know that water is 2 hydrogens and 1 oxygen. One of the things that is not stressed when you first see the water molecule, probably in middle school, is the fact that your oxygen hydrogen connection points don't actually make a straight line, okay? It's not literally HOH as if you were drawing a number line for algebra class. It has a bend to it. You will see some textbooks refer to it as bent. You will see some textbooks refer to it as V-shaped. So look at your illustration here. One of the things that's true about this particular molecule, and we'll talk more in later chapters about the dots and the other part, is because your oxygen has more electrons to start with, because remember, hydrogen is tiny, hydrogen has 1 lonely electron of its own. Even if you have 2 hydrogens, that means you only got 2 electrons there. Oxygen has more electrons, which makes the pointy end of your water molecule kind of negative. In relationship, then, the end or the opposite side of your water molecule is kind of positive. Okay, so the electrons that are bonding this whole thing together actually are not shared equally. The oxygen is being the electron hog. Okay, it's keeping all the electrons mostly for itself and not doing a really good job at sharing with the hydrogens. Okay, why is this even relevant? Okay, because it makes a water molecule polar. Okay, one side is kind of negative and the other side is kind of positive. All right, bad chemistry professor jokes time. So when you go shopping in the grocery store, you go down the aisle where all the bottled water is sold. And one of the brands that is sold in, usually in gallon containers, is Polar, which I know that probably the marketing ploy is supposed to make you think that, oh, polar as in like from an iceberg, because I'm a chemist. When I look at that and I see it labeled polar, and my brain goes, of course, water is polar. Just a truism, okay, which makes kind of for bad brain connections when you're thinking about those sorts of things. So because we have this sort of lopsidedness to your water molecule, it means, among other things, that despite the fact that water is a little bitty molecule, molar mass of 18, it's a liquid at room temperature. You would think that based upon the fact that it's such a small molecule, it should probably be a gas at room temperature. The other thing that is true is we often use water as a solvent for many, many things, not only in lab, but for life in general. Solvent being the dissolving medium in your solution. So if you are making Kool-Aid, okay, the water is your solvent and the Kool-Aid powdery stuff is your solute, okay? Most of the time we tend to think of solutes as things that could be or should be solid. They don't have to be, okay? If you are making salad dressing, okay, and you want to put 2 different types of vinegar together, okay, so maybe some balsamic with some red wine. Both are liquids, okay, you can mix the 2 of them together. One would be a solute, one would be a solvent. Together they make a solution. So the thing I mentioned toward the end of chapter 3 kind of pops back up again here. As we are making solutions, and we mentioned them when we began to talk about molarity, polyatomic ions, all of those things that are on that table in your textbook, and it's also, there's a whole page of them in your lab book, don't fall apart just because you dissolve them in water. There are other things that fall apart because you dissolve them in water, and also you can make polyatomics fall apart if you do things like add acids and set them on fire and that kind of thing. But just dissolving them in water doesn't make the polyatomics fall apart. So sodium chloride, standard straight up table salt. Okay, drop it in water, give it a stir. What you're actually getting in your solution is a mixture of sodium ions and chloride ions. bonds. How about your magnesium bromide? Now, I know we write it MgBr2, but that's actually not the way the molecule looks. All right, let me see if I can do this. So the molecule itself, we're going to kind of do this and put a circle around it so it kind of looks like an atom. And then bond. And then there's a bromine on this side. And there's a bromine on this side. And so this is why when you drop it in water, it gets cut right here, and it gets cut right here, okay? This is why you do not get Br with a 2 subscript still remaining. You actually get 3 separate pieces. The Mg swims free from the 2 bromines, which are each a separate piece. Onto the polyatomics then. So nitrate is a polyatomic. When I have calcium nitrate, it looks a little bit like my MgBr2 molecule in that the calcium ion is in the middle, and there's a nitrate blob on one side and a second nitrate blob on the other side. When you drop it in water, the bond that holds the nitrates to the middle comes apart. But the NO3 chunk does not. This is very, very relevant to a lot of the middle of this chapter. So a little bit more tonight. We are going to be looking over the course of the next couple of class periods at categories of reactions. We are going to loosely divvy them up into 4 categories: precipitation, acid-base, gas generating, and oxidation reduction, often shorthanded as redox. So this all heads in the direction of an upcoming lab known as the metathesis lab. What happens if you mix magnesium chloride and silver nitrate? Does it precipitate? And the little ID thing there is a question. If you made a precipitate, what did you make? Okay, so we have to start with the idea that when you have these 2 things, they are going to fall apart. So we have MgCl2 and AgNO3. All right, so back to my whiteboard again. All right, so we've got an Mg, and it has its 2 little Cl's. Okay, and then we have a silver, which is another molecule, and its other ion is all one chunk, okay, NO3. So this part gets clipped off, this part gets clipped off, and break it in the middle here. So then down here we have Mg's. I probably ought to capitalize my M, okay, which has a +2 charge on it. And we have some Cl minuses, 2 of them in fact. And we have a silver, which has a plus. And we have an NO3 minus. All right. It's kind of like doing FOIL from algebra. Remember first, outer, inner, last? Okay. The positive, this one will try to stick to that one, because you can't stick positive things to positive things and you can't stick negative things to negative things. It doesn't work. And this one will go back and try to stick to that one. First and last, third and second. You cannot do it as second and third because you are not allowed to put a metal at the end of a molecule. So here's your two options. Here's the two things I might have made. I might have made silver chloride, because like I said, the metal has to be at the beginning of the molecule. And because I have a whole beaker full of these things, it doesn't matter that I am using 2 NO3s in order to construct this molecule, because for one thing, it has to be neutral, but I have a beaker full. Okay, I have a whole bunch of them I can use. We'll worry about the balancing end of it later. So which of those two things did I make? So in reality, if I pour these two things together, if I pour these two solutions together, it will make a fluffy gray cloud inside my test tube. But what did I make? There are rules. So here are the rules. Here are two of the rules. They're the only two we're dealing with tonight. One of the rules says most nitrates are soluble. You can kind of translate that in terms of general chemistry as all nitrates are soluble. That means my Mg and my NO3s are going to kind of sort of play bumper cars. They're going to whack together and then fall apart and keep on going. They are not going to stay stuck together. There's another rule. Most chlorides are soluble except, now this one you do kind of have to leave the most where it is, because there are 3 exceptions. Silver, lead of the +2 variety, and mercury of the +1 variety. Because remember, mercury is weird. Mercury, when it's in its +1 format, always travels with a buddy. So you get Hg2Cl2. Well, I had these two options, okay? Scrolling back up here, okay? I had two options. It could be this one, AgCl, or it can be this one. And so I'm applying the rules. I got to precipitate. Well, it can't be magnesium nitrate. It has to be silver chloride. So as we are progressing here through the middle of the chapter, there are 6 rules. I think I loaded them as a separate file in the page that says like useful handouts. So there's a little document that has the 6 rules, okay? Because the 6 rules are incredibly important for doing precipitation reactions. Eventually, there's some other patterning we're going to look at. And then we're actually going to do these for real in lab, okay? This is one of the actual face-to-face labs, even if they're going to drag butt a little bit on returning us to full-on labs. But this one is one that everybody's going to be doing for real anyway, is we're going to do an acid-base reaction in lab. You're going to do a couple of gas generating reactions. They make bubbles. You're going to do a handful of precipitation reactions. Not only are you going to do the observations, you are then going to write all 22 equations for them. So that is an up and coming thing. And I don't want to get too much deeper into chapter 4 tonight. So homework is due. Thursday at midnight, which means I will grade it over the weekend and then post the answer key probably Monday afternoon sometime, and go over the answer key on Tuesday. And I kind of doubt we will actually finish chapter 4 on Thursday. There's a lot of information in this chapter. Questions? All right. I will see some of you tomorrow in lab. And Colson, you're the one who's meeting me tomorrow?
Yes, I'm gonna meet you tomorrow at 2, right?
Okay, yeah. Okay, I just want to make sure.
All right, perfect. Thank you.
All right. And everybody else, I will either see at regular lab time or I will see you here on Thursday.
Hold on, all right, have a wonderful night.
Thank
Okay.
you.
Other questions?
So yeah, so I went to the Barnes and Noble and Marker Author twice this week, and I called them a couple times. They're out of order of the lab book, but I pre-ordered it, so I think it's supposed to come by Friday.
Yeah, I know that Kaya and Heidi are facing a similar problem in that they placed the order, but it hasn't come in yet. So I have some paper copies of the lab that you can record your data on, and then you can just kind of hang on to it until you get your lab book so that you can eventually do the pre-lab and the post-lab questions.
Okay, thank you.
Yeah, no, this is a problem we're continuing to fight, and I'm aware that, yeah, that we still have bookstore problems. All right.
All right.
Bye-bye.
Thank you.